So in this tutorial we're going to be talking about the half-life of a radioactive source, and by the end of the tutorial you should know what the half-life is. You should be able to calculate the half-life of a sample from a graph, and you should understand the impact of background radiation on that graph. So half-life is defined in one of two ways, doesn't matter which one you use. So you can say that the half-life of a radioactive isotope is the time taken for the number of nuclei of that isotope in a sample to halve, or you can say the time it takes for the count rate of a sample containing the isotope to fall to half its initial value. So either of these definitions is fine, but what's really important is that we're thinking about the amount of time it takes for half of the nuclei to decay in a sample. Now, we have to remember that nuclear decay is a spontaneous and random process. So if you imagine we've got some nuclei of a radioactive isotope here, in this group of nuclei we cannot predict which nuclei will decay next. It could be this one, or it could be this one, it could be this one. We have no way of predicting which nuclei will decay next. We cannot predict when a nuclei will decay. So if we look at just this nuclei here, I've got no way of saying whether that nuclei will decay in the next minute or in the next 1,000 years. The only thing we can say is that on average the time taken for half of the nuclei to decay. So here I've got 24 nuclei, so I could say on average it could take 6 days for 12 of them to decay and for 12 of them to remain, because that's how long it's taken for half of them to decay. If I then just had 12 nuclei left, it would again take 6 days for half of those 12 nuclei to decay. So this brings us to the graph of the half-life, or the half-life curve, or a graph showing the count rate or the activity against time for a radioactive sample. And what you can see is that as time progresses, the count rate here decreases. So over time the count rate decreases, and it's this curve, and mathematically this is an exponential curve. Now, a couple of things to point out from this graph. First of all, whenever you see one of these graphs, you need to check the units on the axis. So here we've got time, and here we've got the count rate in counts per minute. The units, especially on the time axis, can vary from hours to thousands of years. So really important to have a look at the units. The second thing to look at here is that each cross marks a data point, a measurement from an experiment in a lab, and then we've got this smooth curved line of best fit running as close to as many of the points as possible. This is real data that's been measured, and it's got an average line of best fit, so the points don't always lie perfectly on that average line. So here we have another curve. We've got the count rate here in counts per minute, and we've got here the time in days. Now remember, the half-life is the time it takes for half of the nuclei of the isotope that were initially there to decay, and that's the same whether you start with 100 or whether you start with 60. So what we're going to do now is show how we can calculate the half-life of a sample from this graph. So first of all, pick your initial value. So to make it nice and easy to start with, we're going to pick an initial value of 100. So that's where I put my first point. So for the at time 0 here, I've got an initial value of 100. Now half of 100 is 50. So next I'm going to take a reading off the graph for a count rate of 50 here. So that's 50. I then draw a line across. So I've drawn a line across from 50 to where it touches the graph, and then I draw a line down from where it touches the graph to read off the time off the bottom axis. So the time it takes to go from a count rate of 100 to a count rate of 50, which is half, is 8 days. Now what's really good is it doesn't matter what initial values we pick here and here, we should still get a time of 8 days along the x-axis. So whatever values you pick, you should get the same half-life out, and that's what I'm going to show you how to do now. So this time I'm going to pick values of 80 and 40. I've picked 80 just randomly, and I've picked 40 because it's half of 80. So I draw my lines on. So from 80 I've drawn a horizontal line across to where it meets the graph, and then ideally with a ruler you draw a vertical line down and see where it comes to on the axis. So that's for 3 days here. And then I've done the same for 40, so I've drawn, again ideally with a ruler, a line across to where it meets the graph and then down, and that gives me 11 days there. And the half-life is the time between these 2 points, so 11 minus 3 gives me a half-life of 8 days. So you see I get the same half-life no matter which initial value I pick. So the final thing we have to talk about is the impact of background radiation on the graph of count rate against time. So given enough time, nearly all of the nuclei in a radioactive isotope will decay, and what you can see happening on the graph is the count rate decreasing. So over time it gets smaller, and eventually nearly all of the nuclei will decay. However, as you can see on this graph, the line doesn't tend towards 0. It will tail off and carry on horizontally at this value here. And the question is, why does this graph not go to 0? The answer is because of the background radiation that's present all around us. If we conducted an experiment without a radioactive source present, there would still be a background count rate. So this graph is showing that even though the count rate of the sample has gone to 0, it's what this sort of base level here gives you the background reading. So you can use this graph to calculate the background radiation level by reading off this value here from the graph. So that's everything on half-life. So what you need to make sure you've done is make sure you've got some notes on the definition of half-life. Make sure you can calculate the half-life from the graph and that you've got notes on that method, and then make sure you're clear about how to determine the background radiation from a graph showing the count rate, how it varies with time. Go back through the tutorial if you need to get your notes finished, and then we'll do some questions in the next lesson.